SRS facilities rely on dependable electrical distribution systems to provide power to key vital equipment. This course will discuss systems and components that will help you understand the importance of electrical power distribution systems. These are the objectives for this course. The electrical distribution system comprises all the electrical hardware that is located between site-generated electrical power or commercially purchased electrical power and the facility loads. The electrical distribution system provides the power for process loads, lighting, instrumentation, heating circuits, logic and sequencing circuits, operating devices, and air conditioners. The electrical distribution system provides the components to connect and disconnect loads, provides means to electrically protect loads and cables, and provides the necessary instrumentation to monitor itself. An electrical power system consists of four main parts: a generating system, a transmission system, a distribution system, and a power utilization system. The generating system consists of sources of power and associated step-up or step-down transformers for preparation of transmitting this power over long distances. At SRS, the generating system is part of the commercial purchased power system and on-site generation facilities. The transmission system includes high-voltage cables, power poles, and switching stations which connect the generating system to the distribution system. The transmission grid extends across the site. The SRS transmission voltage is 115 kilovolts. The distribution system consists of two or more substations. The first substation reduces the voltage of the transmission lines from 115 kilovolts to intermediate voltages, typically 13.8 kilovolts. The next substation will further reduce the voltage to a typical voltage of 480 volts AC. The 13.8 kilovolt switchgear panels normally have ammeters to indicate the amount of current being supplied from the feeder lines. The meters are used to determine how much electrical load is being drawn by the downstream loads. Standby power is the power supplied to loads when the normal power from the distribution system is lost or unavailable. It typically is supplied from a diesel generator or a battery bank. The 480 volt distribution system has indications associated with the switchgear. The indications allow the operator to determine if the distribution system is functioning properly, verify alarms, and to use the indications to determine the cause of an abnormality. The substation normally will have some or all of the following types of indications. A transformer voltmeter indicates the voltage on the line between the transformer and the switchgear main circuit breaker. A transformer ammeter indicates the current output of the transformer. The meter is used to determine the amount of current that is being supplied by the transformer to the switchgear bus. A transformer demand watt-hour meter displays the highest output power produced by the transformer to date and totals the real power supplied by the transformer over a period of time. And a switchgear bus voltmeter indicates the voltage on the switchgear bus bar. The meter is used to verify proper voltage available on the bus bar. Motor control centers act as a centralized distribution and control point for 480 volt AC components. Each motor control center contains breakers or switches and fuses, motor controllers, instrumentation, and protective devices to control the loads on the center. The power from the motor control centers may be fed directly to a load via a controller, or fed to lighting and distribution panels via a step-down transformer. The motor control centers typically have indications associated with circuit breakers or switches on and off position, and power to the control center. The step-down transformers further reduce the 480 volt AC power to 208 and 120 volts AC. This power is then distributed to various small loads such as lighting, instruments, and standard outlets. Panel boards provide the distribution of power to small loads and consist of panels that contain small breakers similar to breakers found in the home. Some loads are known as vital or essential loads. These loads are electrical components that are essential to the operation of a system that performs a vital function. Generally, indication, control, computer, and protection systems are considered vital loads. When a reduction or loss of normal power occurs, power availability to vital loads is assured through the use of backup diesel generators and by de-energizing non-essential loads. Protective relays are designed to cause the prompt removal of voltage to any part of a system to prevent damage. As soon as an abnormal condition is detected, the relay activates and opens a circuit breaker, disconnecting the defective equipment circuit as quickly as possible. Circuit breakers are mechanical devices used to control power to a load. Breakers typically contain overcurrent devices to automatically isolate the load from the power source when a high current condition occurs. Circuit breakers will be discussed further in the next topic. There are several types of fuses in use. A fuse is a device that protects a circuit from an overcurrent condition only. It has a fusible link directly heated and destroyed by the current passing through it. The fusible link is a current-carrying element sized so that the heat generated by the flow of normal current through it does not cause it to melt the element. However, the fusible link will melt and open the circuit when an overcurrent or short-circuit current flows through the fuse. The approved method of wiring single-phase power is the scheme commonly referred to as the 3-wire, single-phase Edison system. This power scheme uses a center-tapped transformer with the center tap grounded. This provides 120-volt connections on either side, or full voltage, 240 volts, across both sides. The center tap of this transformer is a good example of a system's ground or neutral. The purpose of this distribution scheme is to provide an improved method of furnishing single-phase power at 2 voltage levels, normally 120 and 240 volts AC. This is the method of power distribution used in homes. The simplest 3-phase system is the 3-wire delta configuration, normally used for transmission of power in the intermediate voltage class from approximately 15,000 volts to 600 volts. This depicts the ungrounded delta, normally confined to protected environments such as full enclosed ducts or overhead transmission lines that cannot be reached without extraordinary means. This shows a ground point affixed to one corner of the delta, which effectively lowers one phase's voltage reference to ground to 0, but retains a phase-to-phase voltage potential. So the purpose of this system is twofold. 1. Transmit power in the intermediate voltage class from 15,000 to 600 volts AC, and 2. Protect the other two phases from accidental grounding or lightning strikes in outdoor settings. The center grounded Y system extends 3 current-carrying insulated conductors and an insulated grounded neutral to the loads from the secondary. Its purpose is to provide 208 volts AC 3-phase, phase-to-phase, and 120 volts AC single-phase, phase-to-neutral power from the same system. This system is recognized as the safest possible multi-purpose distribution system for low voltage and is commonly seen in the 208 and 120 volt range in many facilities. System grounds have useful functions, such as maintaining line voltages to ground at specific levels, and can be used to protect the system from accidental grounds or from lightning strikes. This is a typical system used at SRS to transmit 480 volts AC from distribution substations via MCCs to the loads. If a ground were to occur at point 1, the resistance between phases A and B would be almost 0. Since there is 480 volts AC feeding these two lines, current would increase dramatically, causing the circuit breaker to trip. Ground fault currents can be dangerous. Should a ground occur on phase C at point 3, a similar ground fault would occur. But if a ground occurs at point 2, nothing would happen because phase B is already at ground level. This shows the typical 120-208 volt AC system at SRS. In this case, note that a fault on any line at points 1, 2, or 3 would cause a breaker to trip. Phase B in this scheme is not at ground level, so it is treated identically to the other phases. If a 480 volt AC cable feeding a component becomes grounded, the component enclosure would have a potential voltage between it and ground that would equal the line voltage of the system. Should this enclosure be touched by a person, current flow could be directed through that person to ground and cause personal injury due to electrocution. This would be a dangerous situation if either phase A or C were grounded and if the cabinet were not grounded. To prevent this dangerous situation, all of the electrical cabinets have an equipment ground as shown. In this case, if an inadvertent cable to cabinet ground occurred, the current would have a low resistance path to ground, bypassing the person, which is the purpose for equipment grounds. Operators, maintenance persons, and supervisors should take care to note if equipment grounds are solidly in place. If not, this could expose people in the area to unsafe equipment enclosures.